Welcome class to our video notes section on Skill 7 from Unit 3. In this video, we will be learning about how to solve, okay, different word here, solving rational equations. So instead of simplifying now, we're solving because now we have an equation, right? The word equal is in there because equations have equal signs, right? These guys. So if you notice all of our examples, I have an equal sign here, equal sign there, equal sign there, etc., right? They all have equal signs because they are all equations. And what that's going to do is it's going to free us up to cancel out the denominators. Our goal is going to be different here. We're not trying to simplify. We're not trying to add the fractions. We're trying to solve for the variable. So instead of trying to get a common denominator, we're going to get rid of the denominators, okay? So we still start by finding the lowest common denominator because that's going to be our key to canceling them out. But instead of creating a common denominator, we're going to multiply by the common denominator. And that is because we now have this wonderful thing called an equal sign. And we have this wonderful property called multiplication property of equality. We're going to take advantage of that property, okay? What that property says is that you can multiply literally whatever you want to one side of the equation, as long as you multiply that same thing to the other side of the equation. So the thing we're going to want to be multiplying every time is the LCD. We're going to want to do the LCD to the left side, the LCD to the right side, because the LCD is all the common factors and it's all the factors basically of the denominators. So if you multiply by them, it will cancel all the denominators out and help us solve just a basic algebra equation. It's not going to be all crazy with variables in the denominator anymore once I multiply by the LCD. And the multiplication property of equality says, okay, multiplying this side of the equation by something is going to change its value. But that's okay as long as you change the value of the other side the same amount. All we're trying to do now is preserve equality. So when you multiply this side of the equation by the LCD, you'll get a different thing. It'll be a different value. But that different value will be equal to the different value you get on this side because these expressions were equal. If you multiply them by the same thing, the resulting equations will also be equal and therefore will be a legitimate equation for me to solve. Okay, so that is the process we're going to use. Once we multiply by the LCD, we go ahead and solve for the variable, and then we just make sure none of our answers would create zeros in the denominator. So let's walk through the first one. So the way we find the LCD will be similar, okay? It's going to be the same rules that were covered in our Skill 5 video. We start by looking at the different factors in the different denominators, and we write down the common ones. So each of them have an m in common, and we don't need to write it twice. You write the common factor one time. Then you go through and multiply by whatever factors remain. So common factor times the remaining factor, and then you multiply that together. Okay, so my LCD for number 1 is 10m. So I find that first. So I have to get really good at finding LCDs. Okay. But instead of making each of these have a 10m in the denominator, I'm going to do something different with that LCD. I'm going to take that LCD and I'm going to multiply it to both sides of the equation using the multiplication property of equality. If I multiply 4 by 10m and then all of this by 10m, the resulting quantities, though they will be different, will be still equal to each other. Okay? I write it down carefully though because I don't want to lose track of everything. So on the left side, I have 10m times 3m plus 2 all over 5m for my first fraction, plus 10m times 2m minus 1 all over 2m for the second fraction. And then on the right-hand side, I just have 40m. Then this is where the magic happens, right? This is where things get awesome. All my denominators are going to cancel out. Every single one will be gone, okay? There's another name for this, by the way. It's called fraction busting. How awesome is that? That we can just bust these fractions out and then not have to work with them for the rest of the equation. It's such a wonderful thing, and it's all possible because of this lovely equal sign. So then here's what I have left over on the top here. I have a 2 times 3m plus 2 for the first one. I had a 5 left times 2m minus 1 for the second one, and all of that is equal to 40m. Now, there was a 5 left here because when 2 divides into 10, there's still a factor of 5 remaining. The 2 turned into a 1, but the 10 turns into a 5. And then when 5 divided into 10 here, there was a 2 remaining. So a 1 on the bottom and a 2 on the top. So anyways, that leaves us with this really nice linear equation. It's a very simple equation to solve now because it's just a linear equation. I just have to distribute to be able to combine like terms. And then once I've distributed, now I can start adding things that are common. So I notice I've got a 6m plus a 10m, so that would be 16m. I've got 4 minus 5, so that's minus 1, equals 40m. Okay, then I have two options. I can either subtract 40m from this side and that side to get the m's together, but I think it might be better to subtract the 16m from the 40m for two reasons. One, I want to get the m alone eventually, so getting it away from the number is helpful. But two, if I subtract a smaller number from a larger number, my result is positive, which is always nice, right? So then I get negative 1 is equal to 24m, because 40 minus 16 is positive 24. And then all I have to do is divide both sides by 24 to get my variable m by itself. So m ends up equaling negative 1 divided by 24. So what does this mean? What does it mean that m equals negative 1 over 24? Here's what that's basically saying, right? It's saying if I do 3 times negative 1 over 24 plus 2 over 5 times negative 1 over 24 plus 2 times negative 1 over 24 minus 1 all over 2 times negative 1 over 24, what this is saying is that all of that will somehow equal 4. Now, I don't want to take the time to do all that right now because that looks like a lot of work, but there is a way we can check this answer, and I want to show you. If we go to desmos.com, and you can type your expression in here, okay? But you have to use x's. See, here it's m's. Desmos isn't going to understand m, but it will understand it if you put it in as x. So I would type the first one in as 3x plus 2 over 5x. And then the second one I would type in as 2x minus 1 over 2x. So according to our math, we want to see where does that equal 4. Let's give this a different color really quick. Let's make this blue so we can see the difference here. So this graph in red is giving me all of the different values of this expression, right? This expression has many different values depending on what x is. Notice it doesn't have a value at x equals 0. That's where the graph has a vertical asymptote because that's what happens when you divide by 0. But for all other x's, it gives you all of the other y values, and we're trying to figure out like when would that y value be 4. So it shows us right here on Desmos. It gives us that point of intersection, negative 0.042. So let's check. Is that the same thing as negative 1 over 24? And look at that. It is. If I rounded, right, I'd get negative 0.042, which is exactly what that was, negative 0.042. So this shows me that my answer really is correct. When x is equal to negative 0.042, or negative 1 over 24, my output, my y value is 4. Moving on to the second example, I'm going to do a similar process, but I'm going to want to factor each denominator first so that I can find the LCD, right? The lowest common denominator. So it helps to factor first because then we can see if they already have common factors, which I can see these do. They have a common factor of x plus 2. So in my LCD, I'm only going to use that factor once, not twice, right? I'm not going to just multiply these together. I'm going to say, hey, they already have x plus 2 in common, so I only use that once. But then I do need to make sure to multiply by the remaining factor of x. So my LCD is going to include the common factor times the remaining factor, and I'll just leave it factored like this, okay? And then I'm going to rewrite this equation so that it is in factored form. Okay, so let's move this over here. So I have 2 over x plus 2 equals x minus 2 over x times x plus 2. It helps to keep everything in factored form because then it makes it easier to see what's going to cancel. Then I'm going to multiply my LCD to both sides of this fraction, okay? Notice I'm not getting a common denominator. See, I have 1 in the denominator. I'm multiplying by the LCD, right? So it just ends up in the numerators. So then I can see that over on the right side, everything cancels. And then on the left side, the x plus 2's cancel, okay? So then on the left side, I end up with 2x, because this was left over and that x was left over. And then on the right side, I'm just left with what was originally in the numerator, the x minus 2. So then I just need to isolate x. So I need to combine them onto one side. So I'll subtract the negative 1x over here. And then 2 minus 1 is 1x. And so that's my answer. X equals negative 2 is what I get for my answer. Except, this is a gigantic except. Except. X cannot equal negative 2, okay? Because if you look back at this original fraction here, there's an x plus 2 in the denominator, which means if I take negative 2 and plug that in for x in the denominator, I would get a 0. And dividing by 0 is a gigantic no-no, right? It means the y value doesn't exist there. See, when we say that x equals negative 2 as a solution, what we're saying is if I plugged negative 2 in for x, these two amounts would be equal. But the fact is I can't plug in negative 2 for x, because if I did, these two amounts would be undefined, which is not necessarily equal. They just both don't exist. So anyway, there's no solution. Even though I had a solution, it's what we call an extraneous solution, because it was a solution that can't be. Okay, so that's what step 6, that's what step 6 is all about. Check your answer against the restrictions, right? Negative 2 is a restriction, and we have to eliminate any answers that would create a 0 in the denominator, because that can happen. So you might be wondering, like, well, how does that even work? How do you get a solution that's not a solution? Let's check Desmos to see what is happening there. And then I'm going to type the other expression down here in the next line. And that other expression was x minus 2 over x squared plus 2x. And so let's see what's happening. So according to our answer, we have an answer at x equals negative 2. Let me type that in here. X equals negative 2. Okay, so that's right there. It's down here. Notice it has a vertical asymptote at x equals 2. Let me just make that a dotted line so you can kind of see. It's like a vertical asymptote right there. The red graph was this equation on the left, the 2 over x plus 2, which is more of the type of function we've learned how to graph that also has a vertical asymptote at negative 2. So what's happening is they both have a vertical asymptote at negative 2. Like if you look, the graphs like want to be equal. They're getting closer and closer to each other as x gets closer to negative 2, but they just aren't ever going to be equal. They're just going to keep getting closer and closer, like infinitely close, but never quite the same. It's what we call an extraneous solution. So we have to exempt it and say, actually, there's no solution. So always check your answers against the restrictions. Moving to example 3, I see here I've got this quadratic denominator. So before you start multiplying things together, let's factor it, because then we can use the lowest common denominator. So I notice I can factor this into x plus 2 and x plus 1, because 1 times 2 is 2 and 1 plus 2 is 3. And what I notice again after that is like, oh, they are all common factors, right? I don't have to worry about any remaining factors. That'll really put the L in LCD, right? If I can just use each common factor once, then I only need these two factors in my LCD. I don't need anything else. So the LCD ends up not being that crazy. And then what I'm going to do is multiply that LCD to both sides of this equation. But let me rewrite it so that it's not as messy. Let's go down here. So I'm going to rewrite the whole thing. And when I rewrite it, I'm going to rewrite it in factored form, because I just feel like that makes it easier for us to see why things are canceling, where they're canceling, and all of that. Okay, so here's my original equation. I'm going to multiply both sides of that by this LCD. So x plus 2 times x plus 1 on the right side, and then I'll do that to everything here on the left side. X plus 2 times x plus 1, which means it'll have to distribute to everything on the left side. So then let me write all that out. So then I'll end up with x minus 1 times x plus 2 times x plus 1 all over x plus 2 times x plus 1. That's just this fraction, plus 3x times x plus 2 times x plus 1 all over x plus 2. And then that equals all of these, x minus 1 times x plus 2 times x plus 1 all over x plus 1. Now I know what you're thinking. You are probably like, why? Why is this a thing happening in my life right now? What did I do to deserve this cruel punishment? And I don't know. But let me just show you. All of that's going to cancel. Oh, see, isn't that nice? Don't you love this? This is fraction busting right here. This is going to make things a little bit easier. Not 100% easier, but a little bit. That is why we took the time to multiply everything by all of the common factors in the denominator, is so that they would all cancel out. Okay? And so yes, my numerators, I now need to FOIL them out. So on this one, I have x minus 1 left over, plus, and then I have to distribute 3x to the x plus 1. But let me just write it out like this first so I don't forget that. And then on the right-hand side, I will have to FOIL. So that's a thing that we can't avoid. But at least it's just 2 things we have to FOIL instead of 3, because that one canceled. We look for the little silver linings. Okay, so I'm going to distribute the 3x to the x plus 1 on the left, and I will FOIL x minus 1 times x plus 2 on the right. Okay? So on the left, I have x minus 1 plus 3x squared plus 3x. On the right, I have x squared plus 2x minus 1x minus 2. Okay? Now, something just happened. Something happened that we need to pay attention to. I now have x squareds in my equation. That means the equation is not linear. The equation is quadratic. Okay? Game changer. All right? When an equation is quadratic, we switch gears. And our job is to get one side of the equation equal to 0. That's a thing we do when our equation ends up with an x squared, meaning it's quadratic. We get one side equal to 0, okay? So I'm still going to combine like terms on each separate side just because it helps, simplify things a little bit. But then eventually I'm going to get everything on one side. So on the left side, oh, and I also start writing things in descending order. So on the left side, I have 3x squared plus 4x because I added 1x and 3x. Minus 1, because that's not a like term with anything. On the right side, I can add the 2x together with negative 1x. And then I have x squared plus 1x minus 2, because 2 minus 1 was 1. Then, because it's quadratic and I want one side equal to 0, I'm going to go ahead and subtract all of the things on the right over to the left. And I'm going to subtract them from their like terms. Well, in this case, I'm adding it to get it to cancel. So I subtract x squared to get that to cancel, and I subtract it here. I subtract 1x from 4x, and then it turns into 0 here, and then negative 2 plus 2 is 0, and then I add that same plus 2. So I'm using the addition and subtraction properties of equality to move things over. So then on the left side, I end up with 2x squared plus 3x plus 1. And then all of these things canceled to equal 0. So when you add or subtract like terms, they subtract to equal 0. So this is exactly what I wanted, right? I wanted one side equal to 0. So then you have options. You can either factor if possible or use the quadratic formula. That is what we do once we've gotten one side equal to 0 for a quadratic equation. I'm thinking this one's factorable though, because I'm noticing that if I do a times c, 2 times 1, I get 2, and my b value is 3, and I'm thinking I can multiply 1 and 2 to get 2 and add them to get 3. So I think this is factorable. So I'm going to go ahead and factor it, but it's got an a value of 2, so I can't just jump straight to the factors. I have to group everything and rewrite 3x as 1x plus 2x. And all of that's equal to 0. And then it's a quick review of trinomial factoring by grouping. We group the first pair and the second pair, keep that plus sign in the middle, right? We're adding here, not multiplying. And then we pull out GCFs. So I'm going to pull out an x from 2x squared plus 1x That leaves me with 2x plus 1, and then there is no common factor between 2x and 1, so I just write plus 1 times 2x plus 1. And then now I notice I have a common binomial factor of 2x plus 1. And let me move over here. So I will factor that common factor out. The 2x plus 1 can be factored out of both of these parts, leaving me with an x and a plus 1. Okay, so those are my different factors. They're multiplying together to equal 0. So I can set each factor equal to 0. I can go ahead and solve for x. This one needs to get divided by 2. So I get two answers. I get x equals negative 1/2, and then I get x equals negative 1. But remember, we learned in example 2 that you have to check your answers against your restrictions. And I notice I notice right here in the third denominator of the original problem, x is not supposed to ever be negative 1. Because if I plug negative 1 in for x there, I would get a 0, which is bad, right? Not supposed to have a 0 in the denominator. So actually, I cannot let x equal negative 1, right? Except x is not supposed to be that. So I really only have one solution to example 3, and that one solution is x equals negative 1/2. That's the one solution that works. That one doesn't work. So there was like 2 at the beginning, but one doesn't work. So really there's only one actual solution that works, and it's negative 1/2. Okay? Moving on to example 4, I notice again I've got a rational equation, and think of this 1 right here as 1 over 1 so we don't get confused. And also right here where I have a 1 minus x, we can factor that into negative 1 times x minus 1. So we've talked about this in a number of our videos. But when you take a negative 1, when you factor a negative 1 out of a binomial, it changes the signs of each of the things. So when you do 1 divided by negative 1, it becomes negative 1. And when you do negative x divided by negative 1, it becomes positive x. And so what that does is it reverses the order of subtraction. The negative x became positive, the positive 1 became negative, so then 1 minus x becomes x minus 1. Now, why would I want to do that? Who cares, right? Who cares? Well, because it helps me see what my LCD should be. Because now I see, oh, I have a common factor of x minus 1. And I have a remaining factor of negative 1. So my LCD should be negative 1 times x minus 1, the remaining factor times the common factor, which is actually not that complicated. It's a lot simpler than if I just multiplied these to each other. So recognizing that they really have a common factor that doesn't have to be duplicated helps keep our L in LCD, helps keep the lowest common denominator and keeps it from having too many factors. Okay, but let's rewrite this now so I can go ahead and solve. So I have x over x minus 1 equals 1 over 1. And then I'm going to call this right here, so I don't get confused later. This is plus negative 1, because subtracting is really adding a negative. And then I believe that will help me later when I am trying to multiply and all of that. Okay, so let's take my LCD to, or let's multiply my LCD to both sides of the equation. So I took the LCD, negative 1 times x minus 1, multiplied it to both sides. I'm going to distribute it here. And then on the left side, I have negative x times x minus 1 all over x minus 1 equals negative 1 times x minus 1 all over 1 plus, and then negative times a negative is positive 1 times x minus 1 all over negative 1 times x minus 1. So this is what I first get when I first multiply the LCD, and then this is where the lovely magic happens. All the denominators cancel out. And on the left, I just have negative x. So nice. Can't get simpler than just negative x. I'll distribute the negative 1 on the right here, so I get negative x plus 1. And then I just have 1 divided by negative 1, which is negative 1. So the 1 minus 1 equals 0, right? So that just cancels out to equal 0. And then I'm left with negative x equals negative x. And there's so many different ways you could think of this. You could say, well, that's just always true, right? Like you could even divide out the negative ones and get x equals x. This is what we call an identity right here. This is what we call an identity, something where one side of the equation is always equal to the other side of the equation. How could x not equal x, right? The other way you could approach this is if from here, let's go over here. Let's take it back to this part again, is you could just add x to both sides and then you get 0 equals 0, which is another identity. So you might be wondering, like, what does this mean? And this is what it means. It means that every single x is a solution. The solutions would be all real numbers. This is what you would write as your answer. Every single real number, right? We exclude imaginary numbers, but every single real number x, you could plug it in for x and it would be true. It's always true. So what that really must be saying is that this expression must be the same as this expression. This must be equivalent to that. They're just written differently. So if we're not sure if we did something wrong, let's check it on Desmos. So what should happen is that this expression should graph right on top of that one if they're really equal. If they share all of the same input and outputs, then their graphs should map right on top of each other. But let's find out. So on the first side, it was x over x minus 1, I think. Holy moly's, look at that. Honestly, I was a little skeptical at first, I'm not going to lie. But look, if I take the green off, I see the red. These graphs. So this graph right here is the graph of x divided by x minus 1. Okay. If I put the green back on, it goes right on top of it. They literally have every single point in common except, actually, I just realized something. Hold on. It's not all real numbers. It's all real numbers except 1. Haha. This problem almost got me. So they share every single input and output together except negative 1, right? Negative 1 is an excluded value. I almost missed that because look, if you look at the graph, they share every single input and output together, right? Every single x and y matches except where there is a vertical asymptote. Moving on to example 5, I'm looking at their denominators and I'm noticing that they have, one of them is not the same. 2 of them are the same and one of them is different. So when I'm looking for the LCD, I only need to use that common factor one time because it's in common between 2 of the denominators. So I only need to use it once, but I will need to multiply by the remaining factor of x plus 2. Your LCD has to have the common factors and remaining factors of all denominators. Okay, that's the only way this will work. And then I'm going to multiply that LCD to all parts of this equation. But let me rewrite it first so that I can keep track of everything nicely. So it's x over x plus 2 minus x plus 2 over x minus 2 equals x plus 3 over x minus 2. And these are all binomial factors, right? And I'm going to multiply them by 2 more binomial factors on both sides. X minus 2 times x plus 2 over here. And same thing over here. X plus 2 times x minus 2 over 1. And I'm going to distribute it on this side. So when I rewrite all of that, I get this. X times x plus 2 times x minus 2 all over x plus 2. And then here I get 3 factors. X plus 2 times x plus 2 times x minus 2 all over x minus 2. And then I get again 3 factors. X plus 3 times x minus 2 times x plus 2 all over x minus 2. So, I know, it looks so crazy again, but it will simplify. Look, x plus 2's cancel here, x minus 2's cancel there, x minus 2's cancel there. Not so bad, right? Not so crazy. Then I will take the remaining factors and multiply them together, and I need to be careful when I do this. So x times x minus 2 minus... So yeah, okay, we'll be careful with that negative, but I'll I'll FOIL the x plus 2 times x plus 2, and then equals x plus 3 times x plus 2. So on the left, I'm going to distribute the x squared minus 2x. On the right, I'm going to FOIL in here, but I'm going to be careful because once I'm done FOILing, I do need to distribute that negative to everything, okay? So I'm going to do x times x is x squared. X times 2 is 2x. Again, I have another 2 times x, and then 2 times 2 is 4. X times x is x squared. X times 2 is 2x. 3 times x is 3x. 3 times 2 is 6. Okay, got all that done. Now let's be careful and distribute that negative to all of the things, okay? So now I have this, x squared minus 2x. Actually, sorry, you know what? Let's combine like terms so then at least I'm not having to distribute to 4 things. That's why sometimes it's nice to simplify a little bit first. So minus x squared, I can go ahead and add 2x together with 2x, right? I'm going to add that to get 4x plus 4. And then I'll do the same thing on the right while we're at it. I've got 2x and 3x. Those middle terms, when you FOIL, will combine. Okay. So simplify that. Now I'm going to go ahead and distribute the negative, now that I only have to distribute it to 3 things. Nicer that way. Okay, so then I get x squared minus 2x minus x squared minus 4x minus 4 on the left, because I have to distribute all the negative to all 3, equals x squared plus 5x plus 6 on the right. And then I can start combining like terms. I notice that x squared minus x squared will be 0. And I can combine negative 2x and negative 4x on the left. So I will do that, and I'll move my work over here. So now on the left side of my equation, I just have negative 6x minus 4, because there was nothing, no common factor to add to the 4. And then that equals x squared plus 5x plus 6. And then I can combine my like terms again. So, or I should, right? Okay, because this is quadratic. Okay, I have x squared, right? X squared. So this is quadratic. Game changer, right? Game changer. Now the goal is to get 0 on one side, right? Get one side equal to 0. So because of that, I'm going to add the 6x over to the 5x and the 4 over to the 6, okay? So then I get 0 because that subtracts to 0, that subtracts to 0. I get 0 equals x squared plus 11x plus 10. And then I can factor, right? I can factor that into x plus 10 and x plus 1, because 1 times 10 is 10, 1 plus 10 is 11, and the a value is 1, so we can just go straight to the factors. And then they're equal to 0, so I can just take each factor, set it equal to 0, and solve for x. So one of my solutions is negative 10, and the other one is negative 1. And neither one of those was an excluded value. The only things x can't be are negative 2 and positive 2. So in this case, there's actually 2 answers. So that happens sometimes too. So these functions are going to cross each other twice. They're going to intersect each other twice. Last but not least, we're going to finish this off with number 6. And we'll use the same process we've been using. We'll start by looking at the denominators and then breaking them into their different factors. Okay, so I'll think of n squared minus 1 as n plus 1, n minus 1, since it's a difference of squares. And I only do that with the denominators because I'm looking for their common denominator. I don't really worry about doing that in the numerator. Okay, so my LCD already has a common factor, right, n plus 1, so I only need to use that one time. I do not need to use it twice. I just use the common factor of n plus 1 once, and then I have this remaining factor of n minus 1. So this is my LCD, just the one common factor times the one remaining factor. And then I'm going to multiply that to both sides of this. So I'll think of this as n over 1 plus n squared minus 5 over, I'm going to think of the n squared minus 1 as n plus 1 and n minus 1. It'll make it easier to see like what cancels and everything. And then all of that fraction on the right is all over n plus 1. I'll put that in parentheses so we know they stay together. Then I'm going to go ahead and multiply my LCD to both sides of the equation. So over here I multiply by n plus 1 times n minus 1 all over 1. I distribute that to everything, and yeah. Okay, so on the left I have n times n plus 1 times n minus 1 all over 1 plus n plus 1 times n minus 1 times n squared minus 5
all over n plus 1 times n minus 1 equals n squared plus n plus 2 times n plus 1 times n minus 1 all over n plus 1. Okay, this one looks crazy, but it's not so bad. You'll see, it's not so bad. Okay, so nothing cancels on the left, so that's kind of a bummer. But here, both things cancel from the denominator, so that's nice. And then one thing cancels on the right, so it's a little less crazy. So then I have n times n plus 1 times n minus 1 on the left, plus n squared minus 5 equals n squared plus n plus 2 times n minus 1. So this one is going to be kind of a pain with foiling, but you'll see it ends up not being so bad at the end. Just have to get through all the foiling. So this is what I recommend. Whenever you have something like this, that's going to be a difference of squares, right? Same numbers, but opposite signs. Foil those first because it'll turn into just 2 terms instead of 3, which is kind of nice to work with. So this will be n times n is n squared minus 1n plus 1n minus 1, okay? And then plus n squared minus 5. Here, I just need to distribute each of these to n minus 1. So maybe I'll finish on this side first. Let me go back to the left side. So then I have n times n squared minus 1 because negative 1n and plus 1n will add to 0. They'll cancel each other out. And so I have only 2 terms, which is not so bad. And then I can distribute the n to n squared minus 1, and I get n cubed minus n plus n squared minus 5 on the left. Okay, so that's what I have on the left. Meanwhile, on the right, I'm going to distribute everything. So I get n squared minus n is n cubed. N squared minus 1 is negative n squared. Then I do this one. N times n is positive n squared. N times negative 1 is negative 1n. And then this one. 2 times n is 2n. 2 times negative 1 is negative 2. So basically, you just have to distribute 3 times. N squared to each of those, n to each of those, and 2 to each of those. And then combine like terms. So the negative 1n squared and positive 1n squared will cancel. Negative 1n plus 2n will combine to just be positive 1n. So then I get n cubed plus 1n minus 2. So that's where I'm at on the right-hand side. N cubed plus 1n minus 2. Okay, so now I just need to start combining like terms, and you might be thinking, Ms. Lasner, do we have to solve a cubic? And the answer is no, thank God, because watch, when I go to try to combine like terms, they'll just cancel themselves right out of the equation, which is fine by me. So those are gone. So they freaked us out for a moment, but now they're gone. So we're going to just calm back down. It's a quadratic still though, right? Still a quadratic. So I have n squared minus n minus 5 on the left equals 1n minus 2 on the right. So again, it's quadratic. Game changer, right? Game changer. Because of the fact that the highest power of n was 2, that means we need to get one side equal to 0. So I'm going to subtract 1n from the other 1n and add 2 to the 5, the negative 5. These will then subtract to 0, leaving me with a 0 on one side, which is what I wanted all along. And then on the left, I have n squared minus 2n minus 3, because negative 1 minus 1 more is negative 2, and then negative 5 plus 2 is negative 3. So good news, I think this one will factor 2, because if I need two numbers to multiply to negative 3 and then add to negative 2, I could use negative 3 and positive 1. So n minus 3, n plus 1, multiply those together. They're equaling 0. So then I just take each one of those separately and set them equal to 0. And then solve for n. So I get one answer of 3. And then the other answer of negative 1, except, look at this first fraction up here. I was dividing by n plus 1. Can't divide by 0. And if n were to equal negative 1, I'd have negative 1 plus 1 equals 0, and that's bad, right? So I cannot let n be negative 1. So we're going to say, except, I want you to write this really big in your notes, because then maybe you'll catch these things more. N can't equal negative 1. So for that reason, we're just going to say, nope, sorry, that one can't work. This must be the only answer for number 6, right? So this would be the value of n that we could plug in to each side and get equivalent values that are defined and not undefined. So that concludes this video. You can see a lot of different things happen when solving these rational equations. So I'm so glad that we're going to be working on this together in class where I can help you, and I'll see you there.